Our project title is Cybersecurity Enabled DER Management Systems. Our project Cybersecurity Enabled DER Management System focuses on creating secure and efficient microgrid using photovoltaic-wind generation. We utilize distributed energy resources communicating over TCP or IP networks to optimize energy use. The key challenge is ensuring cybersecurity for these DERs, which act as IoT devices. To address this, we proposed a testbed using IEEE 2030.5 protocol, known for its secure communication with encryption and key management. We are integrating the testbed with VOLTTRON for real-time monitoring and control, simulating potential cyber attacks to improve resilience. Additionally, MATLAB Simulink will model and simulate grid behaviors, allowing us to analyze disruptions and security improvements in realistic environments. The system's scalability will help in expanding its use as more DERs are added. Our solution ensures smarter energy distribution, improved grid stability, and robust cybersecurity for smarter grids. We created a microgrid using different DERs and then collects the data from the different DERs to an aggregator. The aggregator will send the data to the server. The server will analyze the data and monitors the data that which comes from different DERs and then sends the control commands to different DERs depending upon the grid conditions. We accomplished this using a platform called VOLTTRON. The VOLTTRON platform will provide client-server architecture for data communication between DERs and server. We additionally created a virtual model for simulating it under different conditions for better grid resilience. Using MATLAB, can we build this system? Yes, we can create a system using VOLTTRON and MATLAB Simulink using IEEE 2030.5 protocol. This system would act like a real microgrid but in a virtual space, and also allowing us to test how secure a smart grid is from cyber attacks. What are the challenges? The challenges that we face while building this system is bringing the tools and programs that which are needed for this system is quite complicated, and also creating fake cyber attacks to the system is complicated. Can the platform adapt to the growing system? As the system gets bigger and complex, it might become harder to manage. We need to make sure it's built in a way that it allows it to grow without causing too many problems. The system that we build will provide better cybersecurity insights for energy vendors and also provides practical knowledge for researchers to study the effects of cybersecurity in DER management systems, and also provides reliable environments for developers and innovators to test new technologies in cybersecurity for improving the security of smart grid in future days. The system will ensure reliable power delivery to consumers without interruptions. It also reduces the cost from cyber attacks since we are using IEEE 2030.5 protocol, and also our system is eco-friendly since we are using renewable energy sources like solar and wind systems for producing the energy. The system is having greater scalability for more DERs and also promotes innovation in smart grid technologies. And it also impacts the entire power generation system. Application that we build can be applied in various areas including energy companies and renewable energy systems, where it can help and manages secure smart grid in integrating solar, wind and other energy sources. It enhances the safety and efficiency of modern energy distribution networks by protecting them from cyber attacks.
As we can see, we created a virtual grid system by using MATLAB Simulink. This is the irradiance and temperature we are getting from the sunlight, and we are converting the sunlight irradiance into DC power generation by through a PV array, and the generated DC power is fed to a inverter which manually converts DC power into AC power and distributes to the grid, and the grid supplies the generated AC power to various loads. As we run the simulation, here we can see the how the irradiance levels and the power output generated by the PV panel. This is the output generated by the PV panel, and inverter distributing the power to the grid is we can see here. This is the voltage we are giving to the grid, and this is the current we are giving to the grid.
Our prototype, we are creating a environment for client-side tapping by using a platform called VOLTTRON. Here we are using some number of agents. The agent is nothing but it is a subset of the client and which serves a specific task or event which is given by the server. I already installed a listener agent. Let's run that. Here you can see it can generate a timestamp data of time, year, month and data, and it can send this data to subscripted server, and the server retrieve the data and display that in interface. We had already installed several number of agents required in our project like this, and we are able to configure these agents to the subscripted server for establishing a communication among them.
On the server side, VOLTTRON manages energy data flow between DERs and the grid. The server collects data, processes it and sends instructions back to DERs. For example, during peak demand, the server can command solar panels to manage output or batteries to discharge. Simulink simulations help us test and validate these control decisions. We use OpenArea VTN server in our project. The VTN server is a central control system that manages communications between energy providers and consumers in a demand response system using OpenArea 2.0p protocol. This protocol enables automated demand response to manage energy loads efficiently, typically in smart grids, allowing the grid to respond to changes in electricity demands.
Now we need to integrate this system to virtual node for automation.